Last time, I introduced the flow structures on a one-dimensional premise frame, and we think about the structures like this. We have a premise frame sit at a certain position, and this stabilization on a certain positions is caused by the supply of your premixtures with a suitable feed-in rate. Actually, as I described earlier, why this premise frame can sit here because of the balance between the supply of premixtures and also the consumption of the premise frame. Actually, the propagation speed of this premise frame speed is equal to the speed of the premixture coming from the left-hand side. This balance, the supply will be balanced with the consumption, then this frame will sit at the origin. And when you have a stationary frame, then you can observe the flow structures, especially if you look at the temperature. This is the very important temperature profile because we use this temperature profile to identify the different kinds of flow region in the vicinity of the premise frame. In the very far upstream region, temperature is low. Actually, it's almost equal to the initial temperature of your premixture until the flow approaching to a boundary of so-called preheating thickness, preheating zone. In these zones, the temperature start to increase and very fast and to reach to the ignition temperature. That means most of the reactants will be dissociated or pyrolysis to those kinds of active species, and those active species will have a more concentration into the reaction system. Since those active species they can react together, then this zone we call this chemical reaction zone. In this zone, the chemical reaction will be complete, and this curve represents a chemical reaction rate. And finally, they complete the chemical reaction, release the heat of combustion. Then those heat will be absorbed by the mixtures itself. Then the temperature or sensible heat of premixtures increase to the maximum value. That means the temperature will reach to the maximum temperature, or we relate to the flame temperature. Later on, for the premise frame, if you do not have any heat loss in the downstream, the temperature of your flame will continuously maintain its original value at the flame front and to the very far downstream side. This is the case for the adiabatic case. But if you do have some heat loss, then temperature definitely will be decreased. But depend on the different kinds of structure, the temperature variation in the downstream will be influenced by the flow structures in the downstream side, or the other effect different kinds of heat loss mechanism. But anyway, after the chemical reaction, that means that when you go to the downstream high temperature regions, then you do not have a chemical reaction occurs in the downstream region. And this is you can justify the different kinds of flow region in the vicinity of premise frame by looking at the temperature profile. Similar way, you can consider the concentration of reactants vary in different regions. For the upstream regions, the reactants for both abundant and deficient reactants, both of them remain the same since they do not have any possibility to have reactions. But when they approach into the preheating zone, they start to have some thermal decompositions and to produce some intermediate species. And those intermediate species will push into the reaction zone to react with oxygen and complete their oxidations combustion process. In this sense, the deficient reactant should be completely consumed just at in the reaction zone and reach to the 0 point, complete diminished at the boundary of the reaction zone and the downstream zones. later on you will not find out any deficient components exist in the downstream region. However, the abundant reactant, they still have some excess species left in the downstream side. And those concentrations, you can detect it, and they will remain constant in the downstream region. Basically, this is the flow structure. I just described it, and I emphasize from the experiment that you will find out when you observe the different kinds of frames, including the diffusion frame or premixed frame. I mentioned if you look at a frame with the yellow color, it represents there is a high concentration of carbon radicals or carbon particles. The other way, if you look at the frame, look like the blue color, that means that there is a high concentration of intermediate carbon monoxide or OH or CH radicals. If they have a high concentration, they will emit the blue color. And finally, I emphasize from the experimental observation, I applied a certain amount of a small water droplets accompanied with the flow, and you can see there is a significant influence on the frame. There is a reddish layer in the downstream of your premixed frame to represent high concentration of water or carbon dioxide, will give you some observation based on the reddish frame color. Now, I think you have this kind of understanding. Now we try to give you some experimental justification from the planar frame sit in the stagnation point flow. As I mentioned, I think you realize the detailed flow structure on the stagnation point flow, and if you look at the flow structure away from the quartz plate, that means the stagnation plane. And in this region, actually, the flow structure can be described very well by the so-called opposite flow solution, and which means if you have a cross sections on in the flow, that means that you fix the actual coordinates along this cross section. You will find out, you do the measurement for actual velocity, they are uniformly distributed along the radial directions, which means when you ignite it, then you will have a planar premixed frame. Why? The reason is for a given premixed frame, usually you will give a concentration for a premixed frame. For example, you will have a 9.5% methane. That means that you mix the methane with air by 9.5%. You can change concentration to the 6.5% for a specific concentrations. Then this frame will give you a specific frame speed. That means that when you have in this experiment, when you have a given mixing ratio, then this frame will have only one propagation speed, and this propagation speed will fit with will balance between balance with the injection velocity. Then, since the flow has a uniform velocity distribution along radial directions, then you can have a so-called planar frame that tell you at any point along the frame surface, along the radial distance, they have the same frame velocity and balance with the local supply velocity. Okay, then this frame sit very nicely at certain positions away from the H-plane of a burner. And in this sense, you will figure out if you want to do the measurement along the actual coordinates, you can change the radial coordinates, but you still have the same results, right? This is a very similar to one-dimensional theoretical model. This experiment basically belongs to the cylindrical coordinate system, is a 2D frame, but in reality, you can find out, since the nature of the actual velocity distribution uniformly along the radial distance, then we can see this is almost a planar frame, and it can be used those experimental observation to compare or have some analysis on the flow structure meditation. And this is the pictures in our experiment. In our experiment, we try to bring two kinds of the seeding particle. One is the magnesium oxide we use in the positive flow, and the other one is the water particle. The different features for water and magnesium oxide particle used in the experiment. Basically, water has a bigger size and magnesium oxide has a smaller size. That means the movement of magnesium oxide is more suitable to represent the motion of your flow. And additionally, in the reaction flow in this flame burning experiment, you will find out water when they approaching to the flame will experience a high temperature transfer. Then the droplets will start to evaporate. Those evaporation will produce a heat loss from the flame. That means that we may produce a large heat loss for the case of using the water as a seeding particle. Now, I just try to mention later on, I will give you two examples. One case for the water droplet as a seeding particle. The other one will be the magnesium oxide, smaller one, for the seeding particle in the experiments. Now, let's look at the temperature profile without any seeding particle. Why we need to have a seeding particle? Because we want to use the LDV system to do the measurement. Then you need to have some seeding particle. Okay, but for the temperature, it's simply we insert the thermocouple along the radial distance, along the actual distance to measure the temperature at different position of actual coordinates. Okay, you can see there is the two case. Okay, if you do not apply water in, simply you just supply the premixture or methane with air with a certain value or injection velocity, then this flame, the premixed flame can be sit, as I mentioned here, it sit planarly at a certain position away from the exit plane of the burner. Then you do the temperature measurement, you will find out here the horizontal axis represents the actual coordinates from the 0, 0 means the origin of this system or the coordinates, and just locate at the exit plane of your burner, and 14 millimeter is the age of your quartz plate. Okay, when you do the measurement, you will find out at 4, Z equal to 4, have a 4 millimeter distance away from the exit plane of your burner. At that point, the temperature is around 20, maybe 24 or 40 something. Here is very close. This is around very close to the room temperature, and then they will keep the same almost until you reach to the here is a 7.5 millimeter. Then you can see temperature increase, right? And here the increase of the initiation of the increase of the actual velocity, the temperatures represents this is the age, the upstream age of your preheating zone. Then the temperature continuous increase to a certain point. You can see there is the upstream age of your blue bright flame surface, and later on you will see there is a flame temperature increase to the maximum point about 9.5 millimeter. At the edge of the blue flame represents actually the ignition temperature, because at this point, at these positions, you have a lot amount of the OH, CH, and the CO radicals. That means you have a large pool of intermediate species. Then they will go to the recombination reactions to produce the carbon dioxide and water later. So this is the starting point to have a strong interaction of those radicals, and to proceed the chemical reaction. after the chemical reaction complete, they will reach to the maxima point, maxima temperature. This is a so-called flame temperature. But in this case, I cannot say this temperature is the adiabatic flame temperature because in the experiment we use the quartz as the stagnation point, and the quartz will absorb heat in the downstream layer. You can see the temperature start to decrease in the downstream region, and until up to here, up to the plate of your quartz plate. Okay. The solid cycle represents a typical flame temperature for a given premixed flame. They change, the variation is corresponding to a previous introduction on the flux structure for one-dimensional premixed flame. Now, the next case, we apply water, the small water particle accompanied with the mixtures, and those experiment data were represented by the open circle. Then you will see the flame positions move to the downstream sites. Okay, what is the meaning of the position move to the downstream site? When you try to change your position, your actual position from the upstream side to the downstream side, represent the actual velocity of the flow reduced. Okay, at the position, this position, the flow velocity is higher than that for this position. You move further, then the actual velocity will continuously decrease. This kinds of velocity distribution, actual velocity variation was justified from our cold flow experiments. Now, if the flame move to the downstream side, that means that the flame speed be balanced with a lower actual velocity, which means the flame speed is lower. Okay. The previous one, without water application, they sit closer to the actual plane. That means they experience the higher actual velocity, higher supply velocity. Then we can identify as a premixed flame sit closer to the flame, to the actual plane, to the actual plane of the burner has a higher flame speed. But for the flame sit in the downstream more, then this flame will have a weaker burning intensity with a weaker flame speed. Okay. Now, when this flame is weaker, then you can see they move to the downstream side, move to around 10 millimeter. Okay, somewhere here. But similar way, the temperature profile still have show you a preheating zone and a reaction zone. Later on, the flame temperature will be reduced in the downstream site. And here, from the experiment, we can see there is a region to show you the reddish color. Here, the reddish color exists in this zone is quite thick, from the 10 millimeter to 10 millimeter, to represent high concentration of water concentration in this experiment. And you do comparison, you will find out overall the temperature profile of the methane premixtures with water is lower than that for methane premixture without water application. This tells you the influence coming from the water. Basically, is a heat loss through the water evaporation. This is the first part that you can see the temperature profile for a given premixed flame, a propagation premixed flame. The next one, we look at the flow velocity. Okay, first one, we do the measurement for the cold flow. Here we apply the water particles and the magnesium oxide particles separately for two sets of experiments. Now the open circle and the open triangle represent those velocity distributions by using water and the magnesium oxide particles separately. You can see from the left-hand side, the figure represents the actual velocity variations around the actual coordinates. The right figure represents the radial velocity around the actual coordinates. Okay. Now look at the left figures. Here, there is a comparison for the experiment data for using water and magnesium oxide. both of them represent the velocity variation is very, it can be described probably by the parabolic curve. Okay, we already has some theoretical analysis on this kind of distribution, right? This is a second order dependence on the actual coordinates. But you can see the actual velocity for the case of the magnesium oxide is relatively smaller compared with that for the water particle. This is basically the reason is water particle is has a large size and a larger actual momentum, and then they cannot go with the gaseous particle. That means that they cannot represent the flow below the actual velocity of the flow. But a magnesium oxide is a smaller, and its relative can be followed with the flow strength, and you can use it to represent the flow velocity actually. And here you can see the difference basically due to their momentum difference. But anyway, they will continuously reduce up to 0 at the edge of the stagnation point flow. We do not have experiment data since there is the the quartz plate has a certain thickness. They will block one laser light, and you cannot do you cannot have two laser light to cross over and to do the measurement. Then you can see there is a region without experiment data near the X-plane of a burner. The other one is near the stagnation plane, the quartz plate. Those caused by those caused by the block of the one of the laser light. Then you cannot have an experiment, but you expect the data will go move to the 0 at the surface of the quartz plate. Okay. And then you move to the radial velocity distribution. Yeah, you can see these two lines, one for the open circle and one for the triangle circles. They are very nicely and can be predicted and compare with the theory. Additionally, you can see for the radial velocity, actually, for the actual radial velocity for the magnesium oxides is higher, is larger than that for the water particles, because as I said before, magnesium oxide has smaller diameters and easier to be to move with the gaseous flow. Has lasers, less inertias, then they can carry. They have a smaller actual velocity, but they have a higher radial velocity. That means that they can bend, follow the flow structures easily. Okay, but anyway, there is the turning point to show you the edge of the boundary layer for the cold flow. Okay, this is the first comparison I want to mention. The next part, we move to the reaction. That means that we ignite it and look at the variation of the actual velocity in the left-hand side and the radial velocity in the right-hand side to see the differences, the different features for these two cases. Okay. Let's look at the solid triangle, because this is good to represent real flow structures, because the magnesium oxide has a small particles and can be simulated to the real gaseous molecules. And you can see here, as you remember, in our previous observation from the temperature measurement, frame is sit around 8.5 millimeter positions, and the edge of your preheating zone is around 7.5. Please remember, okay, this number. And you can see for the case of the Meson premixture mixed with the magnesium oxide, initially, okay, you can extrapolate to the initial actual velocities, and they start to reduce. But this reduction is very the reduction of your actual velocity is has a big difference compared with the cold flow, right? Because now you have a frame sit around here, 9.5. Okay. The premixed frame is look like a stagnation point flow stagnation, but this premixed is not a solid flame. You understand there is the high temperature in this region, right? Temperature high in this point and a temperature low in the upstream side, then you will have a so-called thermal expansion to the upstream side, and then this expansion will reduce the actual momentum of your gaseous flow, which means that the actual velocity will drop very fast, and they will move to the minima point around 8 millimeter. Actually, here, as I mentioned, there is a 7.5 around here, okay, very close the edge of your preheating zone, upstream edge, and here they will reduce to the minimum value, then they will increase to a maximum value around very close to the maximum value at the position of your high temperature positions. Okay. Why this velocity increased to a very large value? For the flow from the mass conservation, you will find out as the temperature increase in this region, then the density will reduce, right? Then when based on ideal gas law, when density reduced, then the velocity will be increased. Okay, this is the typical increasing behavior of your actual velocity to the maximum value. Later on, now this actual velocity, the flow velocity will face the rear stagnation plane, the coast plate, then they will be reduced because the influence coming from the stagnation point, stagnation plane, they reduce to zero here. Okay, this is the typical actual velocity variation. Actual velocity means there is the velocity directions point to the flange surface. It's perpendicular to the flange surface. Okay. In this sense, you can figure out what is the flange speed for this premixed flame. Actually, you realize the determination for your flange speed can be identified at the point of the temperature increase, right? Because there is the temperature, there is a region, the temperature remain constant in this region. The velocity is corresponding to the definition for the upstream velocity, which means you can find out the very close very close position to start to have a small increase of temperature around here. You can use these positions and to do the measurement on actual velocity and use this velocity to represent very upstream velocity, and this very upstream velocity is just balanced with the flame speed, which means in your experiment for a given flame, and you try to measure the temperature reach to the point ready for the increase in temperature. Now at this point, you do the measurement, and you can use the actual velocity, the normal velocity to the flame surface, and use it to represent the flame speed. Okay. By this consideration, you can find out here, somewhere here, you can use this value. It's around maybe around 30 centimeter per second to represent the flame speed of this flame in your experiment. Okay. And the second, we look at the velocity distributions, actual velocity distribution for the case of the water. Okay, this is a solid circle here. And you can see as previous cases, the water has a larger momentum, larger inertia, then they will have keep a larger inertia, actual momentum. Actual velocity is higher compared with the case for the magnesium oxide. But you can see here the influence from the flame, okay, there's still less because there is two reasons to have this kinds of curve. One reason is the flame strength is reduced for this case because the water evaporation absorbs a certain amount of heat from the flame. Then flame speed become weaker, burning intensity become weaker. Then in these regions, they do not support enough thermal energy output. The second is the water still large enough, they do not they still can maintain their inertia. They cannot be accelerated efficiently by the thermal expansions. Then you can see the initially the actual velocity is higher than that for the magnesium oxide case, but they cannot increase too much too much compared with that for the case of magnesium oxide, but later on they still reduced. By comparing these two velocity distribution, so you can figure out when you do the measurements using different kinds of seeding particles. If the seeding particle is too large, those kinds of behaviors cannot be used to represent that for the gaseous medians. But for the solid triangles represented by the magnesium oxide is good enough to represent the actual velocity variations for a given premixed frame sit in a stagnation point flow. Now we move to the radial. We just explained it. I just point on, yeah, this is a 3 point we need to remember. And we move to the some description on the radial velocity distribution. And here you can see for the cold flow, there is the boundary. There is a boundary for the boundary layer. And here's a similar way for the radial velocity distributions. You can find out for the solid triangle representing the magnesium oxide cases, they have a higher movement to the radial positions. Okay, radial directions, because magnesium oxide has a smaller inertia. They will follow with the gaseous molecules. But for the case of the water, they will retain their inertia. They cannot be moved with the gaseous molecule to the outer flow. But they still have some turning point to represent. Now this is a boundary of your boundary layer. You can find out for the, usually we use these positions to define the thickness of your boundary layer, right? For the cold flow, this is simply described by the so-called momentum boundary layer. But here with the frame, then you can see now we need to define it as the so-called thermal boundary layer. And here you find out those kinds of turning points is not corresponding to the position of your frame. Position of your frame is around here. Okay, your premixed frame position is around here, and they tell you at this region, actually when you cross the frame, the radial velocity do not change too much. They just have a continuous increasing behavior, but they do not have a abrupt change. But for the radial velocity, you can see from the edge of the preheating zone up to the reaction zone, there is a tremendous increase of your actual velocity, and this is a typical different behavior. And you can figure out for premixed frame, the flow velocity along the normal directions, actually they will change pretty much. Initially, they will maintain their, if you think about the one-dimensional flow, then the actual velocity, the normal velocity is almost remain constant until they reach to the edge of the preheating zone. Then suddenly they will increase dramatically to high velocities, and later on they will decrease because the influence coming from the stagnation plane. But you remember that the tangential velocity, that means in this case the radial velocity on the frame, actually they do not change too much. Okay, for example, there is the here they tell you at the frame position around here. Okay, the radial velocity in the edge of the premixed frame, upstream edge, maybe they have a 40 centimeter per second. When you closer to passing through the premixed frames, in the downstream side, maybe increase to the 50 or maybe 45. The change of the radial velocity when you passing through the premixed frame, actually they do not change too much. Simply think about it. For a given frame rate, the velocity change on the along the normal direction has a big one, but along the tangential directions, this tangential velocity actually is almost remain constant when you are passing through the premixed frame. And those experiment observation I given you. I gave you basically for the stagnation point flow. Definitely, if you try to do the experiment by use of post-jet flow with identical premixtures from the upper and the lower burner, and you ignite it. This is a cold flow. I already explained it. This is a half of the flow visualization. But when you ignite it for identical two given premixture from upper and lower burners, then you ignite it, you will see a double flame, okay, parallel planar premix flame sit together. There is some edge effect because for the experiment system we have a suction exhaust system. We need to suck out all the products, okay, and prevent the so-called buoyancy effect. Those suctions are coming from the downstreams or coming from the lower burner. Then you can see the flame bend down. This due to the suction on the edge of the lower burner. But we do not have a suction in the upper part. Then you can see there is a bend upward because this is caused by the buoyancy effect, and those flame will anchor by the buoyancy effect to attach the upper burner. This is another normal one. Usually those flame will be bent down if you increase the suction strength in the lower burner. Then these two flame will look like this. But anyway, in the center region, there still remains two flat flames, and they will interact each other. And we call this as a double premix flame in opposite jet flow.